everyone. Thanks for joining us on another edition of the AI Debrief. Today we're talking with Chris Ritter, Director of the Digital Innovation Center of Excellence at Idaho National Laboratory. Chris, thanks so much for speaking with me today.
It is great to be here, Kevin. This will be fun.
Yeah, so I was lucky enough to catch your talk about AI for controlling things at the HPC AI User Forum at Argonne National Lab, and you spoke a lot about your work with digital twins and reactors. So, Chris, can you explain the concept of a digital twin and its significance within the nuclear energy sector? What are the benefits and the challenges?
Yeah, that is a great question. So, in the nuclear energy sector, right, we're working on these microreactors. So, if you think about nuclear as you know it today, right, you think of really large facilities, right, that take a little bit of space, right, and you're physically kind of familiar with the stacks and where they're located. One newer kind of technology that the Department of Energy and Department of Defense is investing in are microreactors. So they're factory fabricatable. They can be shipped on rail, and so they're a lot smaller, and so that's cool from a factory fabrication perspective, but it introduces some new challenges, right? Which is how can we control those reactors with more autonomy, right? So we could have perhaps a remote fleet of operators operating those reactors in real time. So to do that, we need to get to near autonomy of remote operations. And so digital twins are generally defined as, like, the way I like to define them, is like as a living virtual model. So it's a physical asset and a virtual asset that are working together in real time to bidirectionally communicate and kind of operate and predict how something is going to run. So you can think about it in a simple example like an autonomous car, right? There's a model that is running in your car that is constantly predicting all its world around it and then controlling that car based on its surroundings in near real time, right? So that allows you to navigate the streets. In a nuclear setting, you could imagine that technology using autonomy to control that facility with humans, right, in the loop as well, right, to kind of give you the safest operation. But also, if there's a connection delay or something like that too, you always know that you have this autonomous agent that is running on that reactor in near real time along with that asset. So that's kind of where we see the benefit of digital twins for nuclear. And so some other challenges that we have to think about with digital twins are from a computational perspective, right? We need to ultimately build, in my mind, multiple models. So you're probably familiar with physics-informed neural networks, and we're using those approaches. We're also using data-driven models too, and we use them in combination. Because as you know, AI models can be tricked, but if you use multiple models together, we've found that that gets really great results with accuracy. So that's one challenge, right? Is how can you kind of have a multimodal architecture that can be used to predict where the asset's going to control in real time. And then another obvious challenge is connection to the internet, connection to the cloud. Today, you will find reactors aren't really connected to the cloud or connected to the internet. We got the experience to do that with the AGN 201 reactor here at Idaho State University, which is about 45 minutes south of where I'm currently located. And it's an older reactor, like 1960s technology. These AGN 201s, they were $100,000. So almost affordable for a regular person to buy one. They were going to put them in high schools all around the country. And you're like, what could you do with that? Well, we worked with Idaho State researchers to digitize that reactor and put it into a digital DAC, and then work them to stream that DAC in real time to the cloud, and then do our AI predictions in the cloud in near real time. And so that kind of technology is kind of the cutting edge, right, where we can do this kind of cloud streaming. So you won't see your reactor near you connected to the cloud today, but you will see some of these university reactors connecting up. So that's some of the challenges and opportunities that we're seeing today in the controlling things area.
Right on, and I'm glad you mentioned the AG201 reactor. Can you just expand on that a little bit? Like, what can an analog reactor from the 1960s tell us about current and future reactors?
Yeah, that's a great question. So one, it's real. It's a real fissile reactor, right? So it still has radiological elements, even if the core is a plastic core, right? And even though it's a little smaller than the reactors that you're familiar with, it has a regular nuclear control panel. It is under NRC license, so it has all the ingredients of a larger reactor, but in a much smaller sense. And so the way I would think about it is, you typically when you teach a kid how to ride a bike, you don't put them on that mountain bike the first time, right? You give them a tricycle or something like that. So we do the same thing with nuclear operators, right? We typically teach them the first time, right? But they're at school, right? A lot of people are going to learn on a test reactor, right? That is at this scale, small, right? The AGN 201 is 5 watts, by the way. So if you think about that just for a second, 5 watts, not 5 kilowatts, 5 watts. So it's very, very low power, almost zero power. And it's a safe environment for a human to learn, which I think also lends itself well as a safe environment for AI to learn. And so that is really why we're really interested in these university reactors at this stage of where we're at in maturity, because we can do it in a very safe way, and do it in a way that we can mature these algorithms to deploy them in a more broad sense.
Gotcha. And, I'm a big proponent of clean energy from nuclear reactors, and I'm well aware of how safe these machines are. But how can digital twins contribute to enhancing nuclear security and safety?
Yeah, that's a great question. So I think if you think about it today, right, there's a lot on the humans. So there are some automatic controls in facilities and reactors today. But you can imagine, right, if anyone's ever taken like a fault tree or probability class even in statistics, right? If you have only humans, then you get the best of humans. And humans are pretty good, right? As Elon Musk learned with Tesla, right, with his factories, like, wait, humans are underrated. Humans can do a lot of things really well. But if you imagine pairing a human with AI, you can get to a higher sense of reliability, right? Because humans are not perfect, and AI is maybe not perfect in every case. And so if you have the combination of both, you kind of have the best of both worlds in my mind. Now, I will say as a caveat, we still need to do testing and experimentation to see what that kind of balance is of human and AI in the loop, right? We have not done yet those validation experiments to prove yet, right, that is actually a fact, right, that the two combined get you this higher sense of reliability. And I think there's definitely a human factors element to this of how is the AI communicating to the human, if that makes sense, and reporting things. So another autonomous car example, right? I think everyone's trying to figure all this out right now, right, on the car side, right? How do we alert the user? So if you think of like your lane keep assist on a car, it's going to beep at you, right, when you're getting outside the lane, and it's kind of a guardian kind of system, right, to help you. So clearly that's adding value to the user, right? I would imagine if there's been human factor studies, right, that they would prove that, yeah, that's better than not having that beep system. But then there are other cars, I have multiple, that don't beep at you, and they disengage automatically without alerting the user that the AI or the autonomous system hasn't disengaged itself. And so those types of little things, I think, are going to have to be worked out over time. And we're going to have to do some experiments and studies to see what is the best user interface to alert people with what the AI is doing, and then also have the human, right, communicate back to the AI what it's doing. And so there's definitely more studies and research to be done.
Right. And speaking of the human factor that you mentioned there, I saw in your presentation that a digital twin can, quote, predict future temperatures of heat pipe thermocouples, and that the digital twin can then, quote, use predictions to send control requests to the human machine interface. Can you expand on this? And, based on what you were just talking about, what kinds of human-centric checks and balances are involved in this process?
Yeah, that's a great question. So for that particular experiment, that was a couple years ago. And that was using a facility called Magnet, which is a non-nuclear heat pipe test. And that did not run in the cloud. That ran locally in that environment. And so there's a couple kind of things in the mix here. So the data is coming off that facility in real time and coming to a local, computational, basically just laptops, right there inside that facility. And on those machines, they're predicting 10 minutes out the forecast of what's going to happen. And then the AI algorithms are using that forecast to then do a control request back to the system. Now, your question, right, what kind of safeguards are in place? Well, one, those control requests that are sent over go to a secondary computational system that is validating those inputs to make sure that they're in certain boundary conditions and they're not going to cause any kind of weird errors on the machine. Two, if you remember, I can't remember if I showed you a video or not, but we have these HoloLens capabilities, right? So you can put on a HoloLens and you can see in real time, what's happening, kind of like a hologram, right through the machine. And you can get alerts as to what the machine learning algorithm is doing. These are really early experiments, right, of kind of what that looks like. But that's one approach where, the user is always in the loop with what's happening from an AI perspective. And you have a secondary computational system that's kind of validating and checking what's going on. You can actually see a little bit of this again in your car. So if you have lane keep assist, that's one system. And in most cars, you'll see there's a separate system that is trying to keep you in the lane. And both of those systems are separate. So I've actually seen it before where the lane keep assist gets alerted by the other system that it's getting outside the lane, which is kind of funny, but it makes sense if you think about it in those terms. And so, kind of a validator step in the control space is one approach. Anyways, so does that make sense?
Yeah, absolutely, absolutely. And we spent a lot of time talking about how digital twins can affect operation of these reactors, but what are the potential cost savings associated with digital twins and nuclear energy? Maybe like how digital twins can impact the design and licensing phases of these next generation reactors.
Absolutely. So that's an area I'm pretty passionate about right now. So I've had the experience of working on a very large nuclear reactor program before in the design stage. It's extremely complicated. Think 300 engineers working together, and think of a lot of paper. There's a tool. It's Microsoft Word. You may have heard of it. It's very popular in the design of nuclear power plants today. And why is that a problem? From my opinion, when you use Word documents at scale and you're trying to design something that's extremely complicated with tens of thousands of parts, you have one document that describes one system and another document that describes the other. Those interfaces are really hard to manage. So when you're in a smaller project, how do you do it? Well, you keep it in your head, right? And you can kind of memorize where things are. The more complicated the system gets, the harder it is for one person to keep it in their head. So we create lots of meetings to try to get these people to talk together and get the interfaces correct. But in the real world, right, there's a lot of changes that happen, right? Maybe part of your supply chain, you can't get a particular part. Maybe a law changes in the time span that you're designing your plant and need to account for that. Or maybe we thought you were going to have 1 million gallons of water, but now you're going to have 500,000 gallons of water, and you need to kind of deal with that change, right? So maybe you're going to have less modules in your plant design, or things like that you need to worry about. So accounting for that change, how do we do it? So historically, there's a concept called digital engineering. And what that means is if you think about it kind of like a spider web or a mind map, you kind of link all the things together. So when one thing changes, it ripples through and it tells you, hey, wait, you've got a problem here, 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 and here. And you need to go fix that. So it's kind of the computer giving you an alert that you have a problem. Where I think we can go as a next step from that is think about the problem completely differently. So the way it kind of works now, right, is humans will generate the requirements for a plant in Microsoft Word or other documents like that. And then another team, right, a drafting team, right, will build those CAD models. And then another team will run what we call analysis codes, right? And there are lots of them, but imagine seismic analysis, right? We'll shake the plant virtually, right, to see what's going to happen. And then all of that will kind of occur in a little bit of a loop, if you will. And it takes a long time to go through each change, right? You take one small change to a requirement, right, and you're rippling through that whole design. And a lot of different people have to work together, right, to affect that change. So what if we flipped it and changed it completely? And we said, let's give an objective for the computer to solve. We want 300 megawatts electric, and we want it at this size of space, and we have this much water, and maybe we have this much, heat in the area, environmental factors we need to account for. So those are your constraints. Let the computer solve that. What does that mean? Let it design the CAD model for you. Let it run all the analysis codes for you, and then give you options, right? And then the human can pick from those options and then run some of their own analysis to check the work and make sure it makes sense. But think about the problem completely differently. And then it's almost like you could do, if you're familiar with like DevOps for software, you could kind of do DevOps for nuclear, right? So you could have this validation system that kind of checks everything. Does it make sense? And then rapidly iterate. So now all of a sudden you're going to get a design that's been really thoroughly vetted, both by AI and by humans. So you wouldn't have as many design errors, which we think is huge, right? A lot less rework to do. And also the ability to kind of really think what makes the most sense for a particular area, for a particular community, and you get an optimal design at the end too. So how much could that save? Well, we wrote a paper, and we'll provide a link to you, on AI for mega projects. And we looked at hydropower and nuclear energy, and we found that the two are very similar. We saw in the 70s with regulatory changes that like plants kind of almost doubled in their schedule durations and cost overruns. And so we're like, well, what could AI and digital twins do to change that? And so we built a big fault tree and we took every case. So including like acts of God, things that AI is probably not going to solve for you, right? And with that fault tree, we were able to kind of derive how much AI could benefit um, the world. And we found a 21% reduction. And I'll admit, Kevin, like I ran that calc myself the first time, and I was like, oh, only 21%. I was hoping for 50%, right? And then I thought about it, and I was like, well, we need to deploy 200 gigawatts of new nuclear power according to the DOE liftoff report. That is a lot of new nuclear power. If we could save 20% of all of those schedules across, hundreds of new plants, that's a big deal. And I think it's important too to say that AI is going to solve some problems, but not every life problem. And there are other things, of course, that delay projects that are outside of the control of the project team, like environmental factors that could occur on any project, right? So that's why I think that number actually makes a lot of sense. Huge benefit. And in the AI for Energy report, which I'm sure you've already read, in fact, I know you've read it, we talk about this, right? And what the huge benefits could be for the nuclear power industry. But I think that those benefits are bigger than nuclear power and could apply to any large construction project in America. And if you think about construction and efficiency, it's actually slightly gotten worse since the 50s, 60s, which you're like, wait, what? And manufacturing at the same time step has almost gotten twice as good as it was 50 years ago. And so this would be a way for construction maybe to catch up to some of those automation areas that we've seen in manufacturing by using AI as a tool. Does that make sense?
Absolutely, yeah, I agree. I think AI is a fantastic tool for efficiency. It's also not a silver bullet. We need humans doing the hard work, right?
Absolutely. Yeah, I don't want to oversell it, right? I mean, AI is going to definitely change the world, but we're going to need great humans too. So
Right, right. So I saw on one of your slides at the HPC AI user forum that stated that the machine learning model demonstrated, I think it was with AGN 201, had a mean absolute percent error of less than 0.33%, which is apparently quite good. Can you tell me what that is and why it's considered a success?
yes, so that was with the fission battery experiment
Mhm.
that was done earlier. That was that 2022 experiment. So, so that's a big deal because this was kind of a one shot, right? So they had used a facility. So this team, by the way, is pretty awesome. It was Jaron Browning and Katie Jesse who put together this experiment in a relatively short time, right? They had about a year and a half to kind of build out this brand new system that we had never done before. And what was weird about it was usually like the one we did with AGN 201, we got many shots, right? So AGN 201's a university reactor. If we wanted to run it, I'd make a call. The next week, we could get a couple tests in usually, right? So we had a lot of attempts to kind of really refine our algorithms as we were going. This team that actually happened earlier didn't get that opportunity. So they had a facility called Sphere that was kind of like a heat pipe on a table is the best way to describe it. And then I came with them as they're running this experiment, and they had this kind of one chance to get it right. They got an hour and a half because the facility had other things it needed to do after this experiment. They had 1.5 hours total to do this experiment, and then they're out, right? So everyone was kind of curious, will this actually work? So getting an error rate that is less than 0.33% for each thermocouple is a huge deal because they didn't get a lot of opportunities to retrain. So that's why we were really excited about that. Now, the errors that we had with the AGN 201, we didn't disclose publicly, but we can say that in the combination of the two models that we used, we saw high accuracy with that particular experiment as well. But we got a lot more attempts, if you will, on that project.
Right on, right on. So this is more of like a general question, but what are your hopes for the near future with digital twins and nuclear energy? And what about the far future? Do you want to make any like predictions for years and years from now?
Yeah, so I think I'll quote HBC Wire, right? I think nuclear energy is a key part of the AI revolution. I think the two are interlocked in ways that we're now seeing, right? With Microsoft disclosing, right, their use of nuclear power, right, with data centers, and so I think the two have a shared destiny, if you will, and we need nuclear to realize these AI advancements from a power perspective, and we need AI to help get nuclear deployed faster. So I think we'll see more and more of that from a prediction time step. So I think we'll see. one area, right? We've talked about it already, but we'll see, semi-autonomous, we'll call it, design systems for nuclear power plants. That will apply more broadly than nuclear power, right? But I think we'll see that kind of objective constraint approach, and it'll change the whole world for how we engineer power plants. And how do I know that? Well, we have some experiment code that you put in a prompt, it generates the CAD model for you already, and it does some analysis on its own. So we know it's possible. It's early, low tier level, but we're seeing that already evolve today. The second thing is, I think, just like with aircraft, right? You imagine drones, right? There are remote operators. I think that's a foregone conclusion. You're going to see remote operators for power plants over time because it just makes sense, right? You can get a really highly qualified team together in a remote facility. But to make that possible, you're going to need some kind of guardian system, right? Some kind of system to warn you that you're outside of that lane. And so I think we'll see that, over the next, we'll say decade, right? We'll see systems like that come alive. And then the third thing, which we haven't had a chance to talk about, is I think you'll see more autonomous experimentation in the laboratories themselves. So like our latest facility, SPL, it's what we call a post-irradiation examination facility. And there's still a lot of humans that kind of control these arms that come down. And you could imagine AI helping, right, with autonomous experimentation. So we could see more rapid qualification of fuels and materials, which I'm really excited about. I think that could, kind of propel technology forward. And that's, of course, something that the labs are very keen in doing. And then in a longer time step, right, I think you'll see more and more autonomy on design. I think you'll see more and more autonomy in operations, right, to the point where maybe we get to full autonomy one day in the distant future. And maybe we get to the point one day, too, where we have labs that are just running 24/7, 365 on their own, constantly looking and searching for the best materials and the best fuels. And the humans, we're still giving them input of what we want them to search for, but they're kind of constantly on the look for the latest technologies that we could use. And I think we'll see a lot more of that. And I think some people are like, wait, what about, humans? And I think humans are still going to be essential to manage all of this and make it possible. And if you think about the amount of new jobs that are going to come from 200 gigawatts of new power, there aren't enough people out there to hire. So I think you imagine AI really as a tool to supplement and accelerate us into the future. So obviously, I'm super optimistic of where we're headed, but I think we're already seeing some early results in this technology.
I agree. I agree. Well, I think I learned a lot today, and I know our audience will too. Chris, thanks so much for speaking with me today. I really appreciate it.
Yeah, thanks a lot, Kevin. Happy to come anytime.